Section 1.2, again continuing to discuss vector analysis. 1.2 is about differential calculus. I'm skipping the first part of that section, going to 1.2.2, which deals with the gradient. Consider a function of x, y, and z. For example, the temperature versus position. You're at a certain point and you're going to make a small displacement. What happens to the temperature? Well, there is a theorem that says that the infinitesimal change in the temperature would be equal to the partial derivative of temperature with respect to x times your infinitesimal displacement in x plus dt dy plus dt dz. We can move in an infinite number of directions in our small displacement, but we only need to know these three derivatives, the derivatives with respect to x, y, and z, and we can figure out how the temperature will vary regardless of the direction we make our displacement. That's very good. Notice that the same quantity results if I form the dot product of two things. The first thing is dt dx x hat plus dt dy y hat plus dt dz z hat, and the second quantity in the dot product is dx x hat plus dy y hat plus dz z hat. That's our infinitesimal displacement vector. And so this thing in the square brackets, the first item in the dot product, is something interesting. That's called the gradient of t. So if I take the dot product of the gradient of t with the infinitesimal displacement vector, it gives me the infinitesimal change in the temperature. So let's make this official now. We're going to define the gradient of the function t. I even put arrows on the del operator. The gradient of t is a vector. And notice, when you're done taking the derivatives of t with respect to x, y, and z, you're probably going to still have a function of x, y, and z. So just to make sure, the gradient of t is not a constant necessarily. In general, it is a function of x, y, and z as well.